Hi everybody and welcome to Permaculture Malaga. It's been a really long time since the last video and I've been struggling a lot in what to put into this video because so many things have happened since the last video and I wanted to update you on everything, and I also wanted to get on with the analysis. So what I've decided is I'm going to make a video with the sector analysis this time, and then later I'm going to make a video with all the updates that have been going on since the last time. So in this episode we're going to look at the weather and start the sector analysis. Now somebody pointed out to me that the solar angles I did in the first site analysis actually belong to the sector analysis. And this is correct. The site analysis only deals with what is on site, whereas the sector analysis deals with all external factors. So the solar angles should have been in the sector analysis. Now I'm probably going to make some other mix-ups where I mix some sector analysis and site analysis together. But I'll try to point out when things belong to the site analysis and when things belong to the sector analysis. And in the end, you need to do both, and you need to compile all the data together, whether it's for yourself or for a client. One thing goes with the other, so you have to make both analysis. But yes, it's correct that the solar angles belong to the sector analysis. And today we're going to look at another external factor, and that's the weather, which is obviously part of the sector analysis since it's very external. So when you're looking at the weather, you want to gather your weather data. Usually you can go online and you can get the weather data for your local area. This usually comes from an airport or a meteorological station. If you can't get it online, you can usually go to your local meteorological authority and request the data. They will usually be more than happy to send it to you. What you should be aware of is your source, because sources can be misrepresenting and the data can be biased. That is not to say that the data is wrong. The data shows what's been collected. But if it's an airport, even though you might be living right next to it, the airport might be on the other side of a mountain. It might be located slightly different from you, slightly away from you. So you have to think about where the data is collected in relation to where you are. So for instance, I found the data from the Malaga airport, which is only a few kilometers from the finca, and that makes it somewhat equal to my location. Even though the airport is located down in the valley, we're located 200 meters up on the hillside of the same valley. The airport is located very close to the coast. And we're located a couple of kilometers further inland. And you have to know these things to know when the data is representative of where you are or when the data is not. I'm going to show you a couple of examples where the data is slightly biased, I would say. And again, bias doesn't mean it's wrong, it just means it doesn't represent what you necessarily need. So let's have a look at the data. So here we have the data from the Malaga airport, and what's really nice about this is that they give you the raw data. They give you all the years back to 1973, and you can drill down on each individual day and get the raw data for each individual day, and you can also get the annual averages for every year. I didn't collect it directly from Malaga Airport. I collected it from a site called tuchiempo.com, but I'm pretty sure that you can also get this from the Malaga airport site. And when you have the raw data, that's actually the best, because then you can make your own analysis of the data. You can make your own graphs. You can look at the data as it is, instead of someone having interpreted the data. Usually when you look up, for instance, the annual average precipitation in Malaga, you get about 540, 550 mils. And that's not wrong, but it just doesn't show you the whole truth. So here on this sheet, I have put in the data for every year, the average temperature, maximum temperature, minimum temperature, precipitation, wind speed, rainy days, snow days, thunderstorms, fog days, tornadoes, hail, basically all the data that was available. And I'll just make this a bit bigger so you can see. And at the end, I've calculated the average. Now, if you go to precipitation, which is this one here, you can see that, yes, the average precipitation is 546 millimeters. But as I'll show you on the graph, that's not very representative and not a very useful number. What is also good is to calculate the average over the last 10, 5, maybe 3 years, because those are going to be closer or more likely to resemble what the next year is going to be like than something that climate data from 30 or 40 years ago. And those are the columns, rows underneath here. And you can see that they vary slightly. This is the temperature. These are the maximum and minimum temperatures, and you can also see that the precipitation varies. The wind speed doesn't vary that much. Rainy days varies a little. Snowy days go to 0, as do tornado days, and so on. Now, the next thing I've done with this data is put it into graphs over here. So let's have a look at them individually. The blue line is the actual data, and the black line is the trend line I've put in on the data. And what you can see here is that the temperature is going up from about 17 degrees to about 19 degrees over a period of 40 years. I'm going to come back to that, because this is some of the biased data I was talking about before. The same goes for the maximum temperature and the minimum temperature. Now, here's another interesting graph. This is the annual precipitation per year. Now, on average, yes, you get about 540 or 550, which is about here, just under the trend line. And you can see the trend line is slightly increasing. But what you see here very clearly is that there's an enormous variation in the precipitation from year to year, all the way down from 200 mils to 1300, which is 1.3 meters of rain in 1 year. So when you're doing your water calculations later, this is very important information. If you just had the 546 mils a year, you could do your water calculation, but you wouldn't get the full picture, and you might end up being lacking water some years and not buffering enough water in high rain years. Now I'm just going to go over all these graphs briefly, and then we're going to come back to some of them. Again, annual average wind speed, I've converted this into meters per second, so that's actually useful because the data was in kilometers an hour. And it's roughly remains average. Also, the number of days of rain during the year, they vary, but they go almost always between 60 and 80, so that's kind of fine. You can use the average day there. Total snowy days per year seems to be going towards 0. Now this is subtropical, so we don't go below freezing. So I actually don't know how and why it would snow here, but apparently it has been snowing in the past. Thunderstorms also varying quite a lot. Fog is also very interesting data to have. Generally, the most important data is your precipitation, but wind speed, temperature, fogs, rainy days, the more you get, the more you can get a clearer picture of the climate. But really, precipitation is the most important climate data you can gather. But if you're, for instance, in an area with very low rainfall but high fog, you could, in your design, consider doing a lot of fog collection for rainwater or drinking water. So the more data you have, the more you can do. And finally, tornado days. I'm not quite sure what the definition of a tornado or funnel cloud is, but apparently there have been 3 days over the last 40 years with that. There's probably some meteorological definition of that. Hail also seems to be going decreasing, just like the snowy days. So let's go back to some of the data. Now, let's look at the temperature data. If you just look at this graph, you would say, wow, temperatures have been going up 2 degrees over the last 40 years. That is a lot. That's really a lot. And then you have to think and say, why? Why are temperatures increasing 2 degrees over 40 years? That is extremely much. The answer lies in something called the heat island effect. In 1973, when this data begins, there was one terminal at the airport. There was one high-rise hotel or building at the whole Costa del Sol outside of Malaga. There were no motorways. Everything was farmland. Now everything is built up. You have high rises along the whole coast. You have motorways crisscrossing the area. You have massive new terminals, new runways at the airport. You have motorways all over the place. And when you build up an area, you get something called the heat island effect. That is, you get a lot of hard surfaces that can absorb the heat as thermal mass and radiate it out during the night. You also get a lot of reflection on your heat. You have surfaces that can reflect heat back and forth and generally heat an area. Now, heat island effects can be different from place to place in how they actually affect the place, but generally, the more you build up an area, urban area or with infrastructure or anything, the higher the temperature goes. So it's not that data they're collecting is wrong. It's just not representative of where we are, and we're only a couple of kilometers away. but we don't live in a built-up area. So had this data been measured at our place, it would not have looked like this. So when you see something like this, you also always have to ask, why is that happening? What's going on here? And this is simply what you're seeing here is Malaga and the whole Costa del Sol going from a smallish backward town with no hotels, no tourist industry, nothing, to the hotspot of the tourist industry for all of Spain virtually. This is where everybody goes from all over Europe to go on holiday in the summer. So that's what you're seeing in the graph here. And that means we actually can't use this data. This does not represent something useful for us. We can't say, well, if we subtract this and do that, then we might get something representative. We don't have non-biased temperature data. So essentially the first three graphs here with temperature data, we can't use them for anything. Now if we look at the precipitation, you can see this enormous variation as I talked about before. But what you also can see, I've tried to show it here with the red line on the graph, is there seems to be a pattern. Now we always look for patterns in permaculture, and there are also patterns here. It seems to be approximately every 7.5 years that we get massive rains, high rains. Not always the same height, but rains, big years with very much rain seem to happen about every 7.5 years. So my guess, and I'm not a meteorologist, and this might just be a far-fetched theory of mine, is that the next massive rain event is going to be somewhere around 2017, because we had the last big one in 2010. Now we did have a very rainy winter also in 2012, 2013, that winter. Whether we reached the 1 meter mark, I'm not sure. But these massive events, I'm predicting, I won't put any money on it, but I'm predicting that it's going to be about 2017 and we're going to see another massive event of rain. So there's probably some global weather phenomenon that's cycling around and comes back every 7-ish years to produce this massive rain event. Now that's very valuable information, because if you just had the 546 millimeters, you wouldn't be able to see these kind of things, and you would be able to prepare for them. Now, what else I've done is I've drilled down to every year. Yes, 2014. I don't have 13. I don't have the whole year. I only have until October. And you can, as I said, you can drill down and you can actually get the data for every single day. Now I've only graphed the interesting data, which is the temperature and the precipitation and the wind. And the blue line here on the temperature graph is the average temperature, and the red line is the maximum temperature, and the green line is the minimum temperature during that day. And on the precipitation graph, the blue lines is the precipitation each day, and the red line is the humidity generally. And on the wind graph you have the blue line is the average wind speed, the red line is the maximum wind speed, and the green dots are the wind gusts. Now these haven't been converted into meters per second, they're still in kilometers per hour, so it's really hard to judge what speed that actually is, because I have no relationship to wind speeds in kilometers an hour. Now I've done this for the last 5 years, and you can see they all seem to be fairly similar. Hot in summer, cold in winter. Wind seems to vary more during the winter time and not so much during the summer. And you have the rain spread out across a couple of months around the winter season. And again, 2011, you're going to see the same pattern here. Hot summer, cold winter, more spread on the wind speeds in the winter time, and again the rain across the months surrounding the winter time. I'm not going to go into detail on all of these. I've then put them into 5-year averages. So this is the average from the last 5 years. And you can see they follow a nice pattern. Notice that this graph starts at November 1st. And again here, the wind varies a lot during the winter time and not so much during the summer. And again, we can see that the general rain pattern is over the winter, starts somewhere around September, October, goes up, peaks January 1st, and goes down again. Now, as I said, the most important data you want to collect is your rain data, your precipitation. And what I've done here is I simply taken the rain for every day over the last 5 years and plotted it into one graph. Now, let's see if I can make it bigger and still fit on the screen. Nope, can't do that. Okay, I hope you can see it. Now, this gives a different view, because when we calculate annual average precipitation, we have cut the year in half at January 1st. But nature doesn't know it's January 1st. And if you have your rainy season during the winter, you're actually going to cut your rainy season in half and have one part rainy season in one year and the other part in the other year. So let's say you have a rainy season that starts with a lot of rain and then slows down at the end. And the next rainy season has a slow start and rains a lot at the end. What you're going to see is that the year in between those two rainy seasons will look like a year with very little rain. But the two rain seasons might have exactly the same amount of rain. They're just distributed differently around January 1st. So average annual precipitation, or generally annual precipitation, will not necessarily give you a true picture of your water, of your precipitation, and thereby might skew your water analysis later. Now, how much water do you need to store? How much water do you capture? Because you're looking at this date that's set at January 1st, and that's where we cut and that's where we measure. But the rain might be spread out over the winter season, which starts at, or the rainy season, which starts at typically around November and goes into February. So what I've done here is I've simply plotted each and every day 5 years back and the precipitation. And you get quite a different picture. The first thing I've done is I've calculated how long, when does the, I'll just zoom in because you probably can't see this. underneath I've set the date. When is the first rain event and when does it stop? How long does it last? In this case 5 months. And how much rain did we get in the rainy season? Not in the year, in the rainy season. In those 5 months. That's 555. And the next one is from October to May, 6 months, and we get 995. And so on. August to May, 798. October 24th. April, 279. And then again here we have September to May, 7 months, 701, and the next one started, the current rainy season is started on September 28th last year. So what I'm doing is I'm looking for patterns. I'm trying to see if I can see anything that makes sense to me that I can use. First thing I see is that the rainy season varies from 5 to 9 months. And the second thing I notice is that the length of the rainy season has nothing to do with how much precipitation you get. For instance, the rainy season winter 2011-2012 was 7 months and we only got 279 mils, whereas 2012-2013 was also 7 months and we got 701 mil. So the length of the rainy season doesn't tell me anything about how much rain there's going to come. Now, why do I want to know this? Well, it's nice to know how much rain is going to come. Say I'm sitting there in October thinking, okay, now it's the first day of rain. I wonder what this rainy season is going to be like. Now, if I have some indicators, I might be able to make some rough guesstimates as to what this rainy season is going to be. But apparently the date when it starts, the length, does not tell me anything, because there is no correlation between the amount of rain I'm getting and when it starts or how long it lasts. So there's no correlation. What I do see is, now I'm going to zoom out again so you can see the whole graph. What I do see when I look at the graph is a pattern. You have to look, but there is a pattern. First of all, the rainy seasons are somewhat bell-shaped, which is to be expected. You have like a start coming up, and then you have a tail going down. You have a start coming up, tail going down. This one is a bit awkward, but you're going up and you're going down. And here again you have, now the shape of the bell, the size of the bell, the height of the bell is different, but it's generally that pattern in one way or another. And the other thing I notice is that they seem to be somewhat a mirror image of themselves. That is, if you split down the middle of a rainy season, say here, you get kind of like the same pattern on both sides. Here we have a tail coming up, and then we have some days with very high rain, and you have sort of the same thing. There's only one day on the other side, but still, and the amount of rain you're getting is somewhat the same. Here you see it again. We go up some days with about 20-30 mils, and then a big day goes down, and then we mirror the other side, a big day, and we have a couple of days with around 20-30 mils going down. Now, they're not perfectly symmetrical. This one also, even though it's different bell shape, you have the big rainy days, and then you have a dip in the middle, and then you have big rainy days, and you go down again. So they seem somewhat symmetrical. And they seem to be symmetrical about the center, which is, in this case, around January 1st. This case is also around January 1st. This is also around January 1st. Here we have January 1st here. And here we have January 1st here. So within, say, a couple of weeks around January 1st, they seem to be symmetrical, somewhat symmetrical. So, in terms of being able to predict rain events, what I can say is if I know what the rain event looked like, the rainy season looked like up to January 1st, I also have an idea of what the rainy season is going to look like after January 1st. Because it is likely to be a mirror image of the rainy season that has already been. So there's a prediction tool I can use. And I know what this rainy season looked like until now. I don't have the data to show you here, but there have been very, very few events with some rain and a couple of days in the beginning of the season with somewhat high rains. I mean, we're not talking about more than, I'm guessing here, 50-60 mil. So my prediction is here on the other side of New Year's, it's going to be the same. There's going to be a couple of days with some rain here and there, and then at the end of the rainy season, we're going to have a couple of days with 50-60 mils of rain. So this is going to be a very, very dry winter. But this is basically things you can do with your weather data once you have it. Again, just to wrap up, the most important data is the precipitation, temperature, wind, fog, nice to have. Look at your data, look at the source, where you're located in relationship to the source. Does the data represent the weather where you are? Maybe you are situated between two sources. You want to collect data from both sources and try to blend them together. Is there data that's biased? Is the data that is absolutely not representative for you? Then you can't use that as a reference. Try to collect data way back into time, because you might see some things that otherwise are hidden from you if you just have average data. And average data is better for the more recent years than over, say, 30, 40, 50, 60 years. Try looking at the data differently, where you don't split it down January 1st, but just look at it, see if you can see some patterns, see if there's anything happening. This doesn't have to be in precipitation, it could be in temperature, it could be in fog or wind or whatever. Is important to you, and the more data you have, the better it is, because you can use this for many things. I mean, there's the water analysis we're going to do later. You need the water data. If you have the temperature, that's nice, you can use that. Sunny days, if you're having solar panels. Windy days, wind speed, if you're thinking about wind power. Fog, if you're thinking about fog collection. And maybe you can see things saying, oh right, in this period I don't have precipitation, but I have a lot of fog. Maybe I want to use fog collectors. As much data as you have, but don't overdo it. Keep it simple. Look at the things that are important for you, and maybe later you need to come back and do some other calculations which weren't apparent in the beginning. But otherwise, this should wrap up this episode. Hope you've gotten something out of it, and soon I'll do a general video on our updating you on everything that's been going on. Thank you for watching.